All right, welcome back. Today is February the 2nd, and we are celebrating being back in the classroom. And with that, we're going to continue here on NMR spectroscopy. This is the last slide that I talked about last time that we met. And I was teaching you the different aromatic splittings, all right? And how to identify, differentiate when it's monosubstituted, when it's disubstituted. So when it's monosubstituted, you will know immediately if you have a spectrum that has a multiplet that integrates for 5, you know that's a monosubstitution because a benzene ring has 6. You lost one proton, so there must be some sort of attachment there, leaving 5 protons in the ring. Now, if you have disubstitution, that means you lost 2 hydrogens, and then you have 3 different variants. You have the ortho, the meta, and the para. All right. So I taught you also that you have to identify these 3 variants by looking at different neighbors that each of these protons have. And so we learned that ortho will produce a doublet, triple pattern. The meta will produce a singlet, singlet, double, triple pattern. And the para, which is the easiest to spot, will produce a double pattern, which will integrate for 2 hydrogens each of those peaks. All right? All right, so now I'm going to teach you something new, and then we're going to start like analyzing spectra. We're going to do that until 10:40, so we'll have time. All right. So before we do that, I'm going to teach you now how to identify the W coupling, which is very important in proton NMR, and then we'll do carbon NMR, and then we'll do some unknown practices. All right, check this out. So the W coupling works like this. Notice that, for example, you have A to C. From A to C, you will see that there is, like I'm looking at ortho. So if I look at the ortho, there is a W coupling, which is called a long range coupling, that goes from here to there. So that's an upside down W, right? So A to C, for this case, will have a W coupling. So the signal for A, which is already a doublet, will be further split. Each peak of the doublet will have a little crown. Meaning each one of them will split a little bit. And so now you'll have what is called a doublet of doublets. All right? You understand that? So maybe if I pull that other, let me pull that. Let's save time, and you probably have seen this already. Let me pull that from the winter package that I prepared. And just plain that from there. Yeah, let's do that. Yeah, let's talk about the W couplings right here. And that's the same thing that's what we have here. All right, check this out. Here you have the W coupling. So that's why the mono substituted, it's a mess. You will see just like it's a bunch of peaks right there, like crammed into one little window. But let's take a look at the ortho. So let's take a look at ortho. So I changed the ordering here. But so from check this out. Proton A has a W coupling with HC. So in green. So that means, let me see if I can trace that again. What I'm talking about, I have in green, I have this coupling. So that means that my signal A is now going to be split further. So it was a doublet before, right here. And now it's a doublet of doublets. It's this one right here. This is still A. So each little tip of the peak will be split further. And you will see that this is important for when you do like NMRs that are online and in real life. Like basically what I'm saying is in an ideal world, you expect this, the first set of peaks to happen. But in the real world, what you will see is this. All right, so I don't want you to be confused when you look at this and say, oh, what's happening here? You can still treat this signal as a doublet, but just keep in mind that you have a W coupling, and that means, that helps you, that gives you information to say where I'm going to put this proton, and I'm going to show you why in a minute. All right, so signal B has a W coupling. Also, I'm going to put it in blue here with D. So it goes all the way there. That's a W coupling. So signal B is a triplet, or was a triplet here, and now will be a doublet of doublets. That's why this is represented like that. That's what's happening in the real world. All right. Then C is also has a W range coupling with A, so it goes from a triplet to a doublet. And signal D has a W coupling with B. All right. So it goes from a doublet to a doublet of doublets. But it still looks like a doublet in the NMR. It's just that you have to look for that little extra crown on the top. All right. Let's take a look at the meta one. Let's see. So this is interesting because not all of them will have W couplings. All right, check this out. So for A, proton A, HA will have a W coupling with C. So A has one neighbor, so it's a doublet. In reality, you will see it as a doublet of doublets. It'll be this signal. And then B, does B have a W coupling? Let me see. B doesn't have one. B is a triplet. Notice that B is trapped. It doesn't have anywhere to go to make a W coupling. Because the way B, if you make a W with X, it gets to a group. If you make a W with a Y, it also gets to another group. So it doesn't reach another hydrogen. So B is safe. B will stay as a true triplet. You see what I'm saying? Then C is a doublet, and it does have a W range coupling with HC. All right, so it starts off as a C starts off. Oh, I'm sorry, I'm looking at the wrong one. C has a W range coupling with A, and it goes from a doublet to a doublet of doublets. And then D, it's the most fun of all the signals here. In my opinion, is D. D is the isolated one. Is the one that's supposed to be a singlet, but in reality, you will see a skinny doublet. All right. All right. Then for the para, everywhere you go from H to HA, and from HB to HB, they all both will have double range couplings, and so you have, instead of going from doublets of doublets, you actually have doublets. See what I'm saying? Yeah. Any questions up to this point? Why this is important? So it's important because, for example, especially for like groups like the meta, it helps you to pinpoint with precision, especially if you have an unknown, where the X and the Y groups will go. All right. All right. So I wanted to show you that, and so that's a blown up of the explanation here for aromatic coupling. All right. Anybody has a question? Quick question? No? All right. Okay. So let's do the next slide. All right. So interpreting proton NMR spectra. So notice that for every unknown that you get from NMR, you will get a molecular formula. So in this case, it's C9H12. All right. So the first thing you have to do then is find the DU. So I'm going to show you. When we do an actual unknown, I'm gonna tell you the steps that you need to follow. So let me do this here. All right. So let's see. All right. So let's find the DU. So DU is equals to 2 times the number of carbons plus 2 if it doesn't have a nitrogen. Minus how many? Number X, in this case, is 12. Divide all of that by 2. So what do I have here? 18, 20. 20 minus 12 is 8. 8 divided by 2 is 4. So I have 4. The moment that you have 4, you're dealing with a benzene ring. If you have 5, then you have a benzene ring plus another unsaturation. All right. All right. So check this out. Now let's take a look at this proton here. I have a multiplet at around 7 ppm. 7 ppm, 5 protons in integrate for 5. Notice that one thing though, for your unknowns in the lab, this number is sometimes represented here as an integration. It might say like 5.01. That means the same thing. You have 5 protons on that signal. All right? Likewise, for this one, it will be 1. It might say something like 0.998. That is 1. All right? So keep that in mind. You will find the integration underneath. That's what most NMRs do. But the NMRs that I will give you, the spectra that I will give you, will have the H on the top, because I think that's easier. All right? All right. So another thing that you have to do is, notice that when you have these type of problems, count the number of hydrogens you have. So I have 5 plus 1 plus 6. 5 plus 1 plus 6. That's a total of 12. This number right here needs to match this number. All right? That's very, very important. All right. Okay. So the next thing I'll look at here is that I have a, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. There's 7 peaks here. There's a peak here and a peak here that you have to account for. Sometimes it's hard to see those, especially for one of the unknowns that you have for the lab, number 3. I think that was an experimental NMR. It was not a standard sample because it looks kind of dirty to me. It doesn't look pristine, clean, like the other two do. So that's just my impression of it. But you can still solve it. And I'm going to help you out how to solve them. All right? So here we go. This is a septet. And so I'm going to write it down here, septet. So you're dealing with a septet here. And that means that you have, and this integrates for 1. So we're going to come back to that. So a septet means you have how many neighbors? 6. So you have, so what I'll do is I put a CH and put it in a box. And that means this CH must have 6 neighbors. It could be this, or it could be many different representations. All right? let's say, for example, I don't know which one is it, and I'm just going to draw it right now for sakes. All right? I go back over here. I forgot my 5 in the aromatic. The aromatic shows us 5. That means monosubstituted. And if it's monosubstituted, I know I'm dealing with something that looks like this. And I'm going to put an X group there because I don't know what the X means yet. I just know that I have 5 protons that are aromatic. All right? Then I'll take a look at my last signal here around 1. This, whenever you see 6, that means you are dealing with 2 methyl groups. All right? If you have 12, you're dealing with 4 methyl groups. If you're dealing with 9, then you're dealing with 3 methyl groups. All right? That signal at 0.9 is almost guaranteed it's going to be a CH3. That is the signal with that is most upfield. All right? At 0.9. Well, yeah, it's the most upfield. Yeah. The multiplicity here will be a doublet. What does that mean? It's got 1 neighbor. All right. So I'm gonna box 2 CH3s, and I'm gonna box them. Those when I box something here, that means that is the signal of interest. All right. And then they both will share 1 neighbor, a CH. All right, so I think I'm ready now to put this thing together. Notice that then you can say, all right, basically I will have a benzene ring. Let me write that down here. I will have a benzene ring that will have a monosubstitution, and I need a CH, it's right here, and I need 2 methyl groups. And that's it. I solve for that. All right? So that means we'll have all this. So labeling this. So next thing you'll do is label A, signal B, and signal C. So all this will be A. Signal B will be this one in the middle, your CH. And C will be your 2 methyl groups. All right. Okay, so we're going to be using our chart, our NMR chart, and then we're going to solve for the different signals for this. So let's say A, B, and C. So we have, let's say A. For A, we have 7 to 8 ppms, right? That's from the chart. Maybe I should point out the chart in case. So we're looking at this signal right here. Then it's a chart value. It has a multiplicity of what? It's a multiplet. When it's a mess like this that you cannot assign any shape, just call it a multiplet. All right? It's a multiplet that integrates for 5 hydrogens. B, it starts at what? So we have a CH that is attached to a carbon, but it's also attached to a benzene ring. Which one do I pick? The benzene ring. So the benzene ring starts at what? 2.3 right here. Very good. So we have the signal is a 2.3 plus what? 0.7 because it's a CH. Do we have a beta group there? I don't think so. Yeah, so this will be 3.0, and that's exactly where it is, about close to 3 right there. And we're just predicting. So this would be 3 ppms. It's accepted. that integrates for one hydrogen. All right. Any questions up to this point? You good? All right, let's do C. C will be, C will start at what? The easiest one to spot is C. Is a carbon-to-carbon connection there. 0.9, yes. That's a 0.9. What else? It has a beta group. Very good. Let's spot the beta group there. So if I'm looking at C, there is alpha, beta. It found a carbon that is beta. So we have to add 0.3. That will be equals to 1.2 ppms. And that's about what we have here. So this is about 1. So that right there is about 1.2. All right. So 1.2 is a triplet that integrates to 3 hydrogens. To 6 hydrogens. Oh, I'm sorry. I'm looking at the wrong thingy here. Sorry. It's a doublet. Thank you. Doublet disintegrates to 6 hydrogen. All right. What is the name for this molecule? Isopropylbenzene. Very good. So we have an isopropyl group. All right. Excellent. All right. So I'm 2 slides before I'm gonna get to carbon. Yes. Yes, absolutely. 0.7. Oh yeah, I did add it right here. For B? For C, what about it? Why didn't add one? No. This signal starts at 0.9. Okay. Yeah, and then you add 0.3 because it has a beta group. Okay. That's all we can do that there. Mm-hmm. So C signal is a CH3 and that's why it's 0.9 or 0.9? Yeah, exactly. It starts at 0.9 and that's your basic signal right here for a C attached to a C. All right. Okay, let me close this. I don't think I need that. And let's move on to the next example. This example does pretty much the same thing. So let's do it again together. So we have C3H8O. All right? So 2 times 3 plus 2 minus 8 divided by 2. That will be my DU. Find DU. 6 plus, that's a total of 0. 2 times 3 is 6 plus 2 is 8. 8 minus 8 is 0. All right. Okay. So I have a total of 1, 3, 5, 8. 8 hydrogens in the spectrum. And that matches the 8 right here. Okay. And you see this peak here? This is TMS. It's a reference peak. Whenever you see a peak that is not integrated, don't care for it. All right? You will find sometimes the TMS shown. Sometimes you will see a peak around 7.24. That is your deuterated chloroform peak. Basically, we need to use a deuterated solvent to dissolve anything like this, a liquid or a solid to run an NMR. What happened with deuterated chloroform is that 99% of it is deuterated, but there's 1%. So this will be 99%, but there is 1% that still shows as normal chloroform, and that 1% will have a proton. All right, and that if you don't have the TMS peak, let's say you have a deuterated solvent that's it's just deuterated chloroform without TMS in it, because they add TMS on purpose. So you have the two references. But if you only need one reference, so if you don't have the TMS, you can always standardize your spectrum by looking at the chloroform peak and typing 7.24. Once you do that, all the shifts will move and they will all be standardized. And then you can reproduce your results the next time you run them. All right? All right. So let's pretend that's there, that we have the chloroform there, because we're going to be doing absolutely nothing with it. So it's fine. All right? Okay. So here we go. So the next thing you'll do is, all right, go ahead and always lay your signals from left to right, A, B, C, and D. All right. So let's put this together. So notice that since I have an oxygen, unfortunately I have the infrared here, but the infrared will confirm this. I have an oxygen, and I have no unsaturation. That means that oxygen must be what? An alcohol. Exactly right. So with confidence, I can say, okay, I have an OH group here that is a broad singlet at around 3.9. So I have an OH group here, and that's my signal of interest. I'm going to block it. I'm going to put it in a box. Then I go to the next signal. Notice that I have what does this look like to you in blue? The multiplicity. A triplet, yes. So I have a triplet. And it integrates for 2. What does the 2 tells me? That is a CH2, exactly. So I'm going to block my CH2 here. And I have a triplet. So I have the following combination. I could have a CH, or I could have, it could be simple, a CH2 next to it, right? Make sense? So I'm going to put OR here, because I'm guessing right now. I don't know. I don't have enough information yet. I do know, but what I'm saying is, like, right now, at this moment, I'm incomplete. So I'm just going to write whatever I think it could be. All right, letter C. It integrates for 2. So what are we dealing with here? A CH2. Yeah, we have a CH2 in the making here. And it has, what is the multiplicity? 6. It looks like a sextet. So it has 6. So this signal, with confidence, I can say this could be a CH3 attached to a CH2 and a CH3. All right? All right. And then, finally, I have a triplet that integrates for 3. So this must be a CH3 that attached to what? How many neighbors will that have? 2 is attached to the CH2 with confidence. Yes. All right. So I think we have this. Also notice that we only have 3 carbons. So this must be an open chain. We don't have any unsaturations. So we're dealing with something that looks like this. 3 carbons. All right. And an OH group. All right, so the question is, do I put the OH on carbon 1 or on carbon 2? So, according to this pattern, notice that that OH needs to be in the end of the chain. But let the carbon speak to you. So, here we go. So, notice that the signal C says it all. C, you have a CH3, a CH2, and a CH2. That is the best pattern that you can have. And those are just your 3 carbons right there. So your OH is meant to be here. All right? Does that make sense? This is the same thing as if you had like CH3, CH2, CH2, OH. But we're advanced. We're going to do the linear structures. All right? Why? Because you want to have speed. On a test, it's better if you do linear structures than dealing with, condensed structures. All right, so let's label this real quick. So this will be signal A. B will be my CH2 here. C is the next one, and D will be the last one. A, B, C, and D. That order. What is the name for this molecule? Just let me it right now. Propan 1-ol or 1-propanol. All right, let's do A, B, C, and D splittings and analysis. All right. So A is an OH. OH, they range anywhere between 2 and 5. All right. So we have 2 to 5 ppms. Short. It's a broad singlet that integrates for 1 hydrogen. All right. See you later. B, it's a CH2. All right. So, but it's attached to what? An oxygen. So what is the signal that it starts with? Right here. Starts at a 3.3. So that's my closest signal there. It's a 3.3 plus what? It's a CH2. Another 0.3. So that's because it's a CH2. I think that's all we can do for that one, right? There's no beta groups. So this is equal to 3.3 ppms. It's a triplet. I'm sorry? Yes. Thank you. 3.6 is a triplet that integrates to 2 hydrogens. Then C is the most interesting signal here. It starts at a 0.9 because it's carbon to carbons, surrounded by carbons. So 0.9 plus 0.3 because it's a CH2 plus what? And where's the beta group? To the right or the left of it? To the right. So it's 0.3 because we have a beta group. In other words, we have alpha, beta with respect to C. All right? And then that's a total of what? 1.5. 1.5 ppms. We have a sextet that integrates for 2 hydrogens. Finally, we have a methyl group, and that is a 0.9. It's a CH3 to a carbon. 0.9 ppm. That's a short value. I'm looking at this again. And I have a triplet, and that integrates to 3 hydrogens. All right. Any questions up to this point for protons? Yes, sir. Yeah, zero means you have a saturated molecule. You only have single sigma bonds. No pi bonds. Yeah, an alcohol it contains sigma bonds only. Yes. All right. If we're dealing with a carbonyl, then we have a pi bond. or if we have a double bond, a C double bond C or a C triple bond C. Those would be unsaturations. And also a ring is one form of unsaturation. All right? You spot that it's a ring because it will tell you that you have one unsaturation, and you will have two hydrogens that are less than the amount that you will get otherwise for the alkanes. In which signal? D is too far away. That's alpha, beta, gamma with respect to D. You got it? From C to B. Yeah, from C to B is the only way you can find a group that is different than a hydrogen or carbon sp3. So we're looking at this signal here. This would be alpha, and this will be beta. For D will be alpha, beta, gamma. So it's too far away. All right. Let's do the carbon NMR. Carbon NMR is just like proton NMR, but all the signals that we know, we're going to multiply by 20. And then we're going to get an approximate number for the carbon signal. All right. Check this out. The thing, though, for carbons, the first thing you have to understand for carbon NMR, it's finding the unique types of carbons, all right? Because you might have carbons that are equivalent, all right? So, carbon-13 NMR is an isotope of carbon-12. Just like deuterium is an isotope for protons, all right? And so, you can use it to determine the types of carbon the molecule has. I'm going to put types in capitals. All right. So, how many types of carbons do you see on the first molecule? Before you think of it, think of symmetry first. All right. So right here, I'm going to trace a plane of symmetry here, and then I can find the answer for that. How many carbons that are different here do you read? 3. So this would be 1, 2 is equivalent with this one, and 3 is equivalent with this one. I'm going to delete this 2. So this will give me 3 different carbons. How about the next molecule? 4. They all are different. 1, 2, 3, and 4. So this will give us 4. How about this one? Do we have another plane of symmetry? Right here. All right. So let's count those carbons now. I'm going to say 1, 2, 3, 4, and 5. So we have 5 different types of carbons. Notice that your molecular formula will say C8, right? Because we have 8 carbons, and how many protons will have? H10. So this molecule will be C8H10. So on your carbon NMR, you only have 5 types of carbons. So that means that you have you have 3 that are equivalent. So these are the ones that are equivalent: 1, 2, and 3. Wait, no, that's not it. 1, 2, and 3. Those 3. Okay. Yeah, that methyl, this methyl matches this methyl right here. So you have 3 carbons that are equivalent. All right. How about the next molecule? Do we have a plane of symmetry? Yes, right here. So how many carbons that are different here? 1, 2, 3, 4, 5, and 6. So that's 6. And finally, for the next one, how many carbons do you read that are different? This molecule has a plane of symmetry like this, a plane of symmetry like this, and a plane of symmetry. Yeah, that's it. So basically only one. So you have one different type of carbon right there. Huh? All right. Okay, sounds good. Next. All right, so let's check out this. So, yes, sir. Yeah, yeah. Yes. Yeah, yeah, exactly. You got it. All right. Um, Notice this. Your alkyl groups here will show between 0 to 50. Your CO and your triple bond C will show around 50 to 90. Your double bonds and aromatic will show between 100 to 170. And your carbonyls will show between 150 to 220. All right? All right. Let's practice some of this. All right? Once I teach you this, you'll be better off understanding carbon NMR. All right. Okay. So let's say I'm going to label this molecule. I want to say, okay, I have A. Notice I'm gonna label the carbons now because this is a carbon NMR. All right. So A, B. Now I'm going to account for the carbonyl. A, B. Then I have C, D. I have a D here and a D here that are the same. E and E. And I have F right here. I have a planar symmetry that cuts between C and F. Right there. You see it, right? All right. So let's assign these samples. These signals. Their approximate carbon signals. All right. Let's start with A. So what would A be? So what you will do is that you take these proton signals, whatever number you get, let's say you have this number, and you multiply it by 20. And that's going to give you an approximate number for where that carbon signal would show up. All right. So A is a CH3 attached to a carbonyl. 2.1. So it would be that one. All right. I don't know why it moves like that. I'm just going to do like that. All right. So this is 2.1. So check this out. 2.1 plus what? Does this molecule have a beta group? Yeah. Which one is it? The phenyl. Yeah. Where the letter C is. So this will be a 0.3 because it has a beta group. So this is total equals to what? 2.4. 2.4 times 20. It's 48 ppm. All right. So my signal A will be around here. I'm gonna put it right there. All right. Let's do B. What is the closest things to that? Here. Anybody? It's one of these two. Which one is the one that's closest to? A hydrogen and a carbon are more similar than a carbon and an oxygen. So I will pick this signal right here, the one for the aldehyde. So we start here at 10. 10 times 20, that's equals to 200. All right, so right at 200, it will be my carbonyl group, B. All right, all we have to do now is to do the aromatic ones. The aromatic ones are from 7 to 8 on the chart values right here. 7 to 8. So if you take 7 to 8, multiply that by 20, we have a range of 140 to 160. So I'm going to do just that. I'm going to take, and I'm going to put 4 lines here. 1, 2, 3, 4. And I'm going to assign those lines now. All right. Which of these carbons, C, D, E, or F, will be dragged the most to the left? C. Why is that? It's closer to the EWG. So that's the first thing you have to apply. So you go C. Then, which one will be the one most upfield of those? The F. Because it's the farthest from the electron withdrawing group. And then the question is E and D. Which one's still closer to the carbonyl? D. So D has to be dragged more downfield, and then therefore E will be the one right there. How cool is that? You can assign carbon NMRs now. Awesome. Let's do one more example. All right. So here we have an alkene. So now we have a double bond group there. So let's label this. So this would be A, B, C, D, E, and I'm going to call these G's because I already have a fluorine group there. I'm going to call that F. That would be confusing. All right. Okay, so A and B, Antonio Brown, right? So the signals for alkenes, it's between 5.5 and 6.5, all right? So let's do that. So we'll say that we have 5.5 to 6.5, multiply that, both of them, by 20, and we get what? 110 and 130, right? If my math doesn't fail me, something like that. Yeah. All right. So A and B will be right around here. So it'll be 110. One will be around 110, and the other one will be around 130. Let's see, 110 and 130. Yeah, something like this. So, what do I have here? Yeah, so which one will be the one that is dragged the most downfield? A or B? B. Why? It's closest to the oxygen. Very good. And then A will be this one. All right, let's do C. What is C? Let's do it mentally now. C is at 3.3 plus 0.3 because it's a CH2. Does it have a beta group? Yes. It'll be a beta group on the double bond to the left. So this will be alpha, beta with respect to that signal. So another 0.3. So that's a total of 3.9. All right. So I got 3.9 times 20. That's equal to, I think, 78. So C will be 20. Wait a minute. Yeah, 78. C will be right here. All right. D, let's do D. So D is a 2 point, let me see, is a 0.9, right? Starts at 0.9 plus 0.3 because it's a CH2 plus 0.3 because it has a beta group to the left. Alpha, beta, I find an oxygen. So therefore it's 1.5 total times 20. That's equals to 30 ppm. That will be right here. This is D. G, let's do G now. All right. G. Check this out. Yeah. So G is a CH3 attached to a carbon, and it doesn't have a beta group. So it's 0.9 plus 0.3 because it's a CH2 group, because we have an F group there. Therefore, it's 0.9 plus 0.3, that's 1.2 times 20. This equals to 24. 24 right here. DG kind of reminds me of Dog or Snoop Dogg. All right. And then we have E. E is what do you expect? E is gonna be dragged downfield or upfield? Downfield, because it's next to fluorine. Fluorine is super electronegative. So the signal starts at what for fluorine? 4.2. So we got 4.2 plus what? Exactly 0.7, because it's actually it's a C. It is not a CH, but the closest would be 0.7 exactly. So 4.2 plus 0.7, because it's closest to a CH, and then it would be 4. Wait a minute. Actually, just 4.2, because it's not a CH. Just it's pretty much a sharp value at this point. 4.2 times 20, that's equal to 84. So it'll be right here. So this will be E. And we have finished our carbon NMR. All right. So we have time for, so we're going to be doing this spectrum. So actually, I'm going to do the packet that I have first. And this is what I'm thinking of. I think what we should do, also I wanted to show you something real quick. I might have to ask you to sign up again on different Pearson. Let me see. My course is this one. Let me show you something here. I was trying to do the integration with my labs and Canvas, and apparently I cannot use that the Pearson number that I gave you. Check it out. So I click on it, and I have created a new one. So if I go to my courses, I have now two. Notice that this one right here has a link, but it doesn't have, oh, if I were enrolled here, oh, good. So I need this 25 to move over here. So I will send you the information to pick this. You haven't paid for the registration, right? Or have you? And even if you have paid, I think you should be able to just move to another room. So I'm gonna have to cancel this one because this one's the one that I could link. Just some heads up. I will send you information today. Maybe not today. Maybe tonight, because today is a busy day. Anyway, but what I was thinking for in terms of homework, if you do the packets that I sent you and show me proof that you did them, I think that's enough for homework. Let's do that for the first two homeworks, because you have a lot of stuff here. I'm gonna go through some of the NMR IR example packets, but you have packets A, B, C, D, and E. Plenty of work for you. If you just send me a PDF, or scan them, or make a copy, show it to me somehow, or bring it to me. I'll give you the point for the homework, and I will not grade it. I'm just look at it for completion, trusting that you did them, and I'll give you 20 points. We'll do the same thing for the mass spec. Maybe that one I can collect actually, because it's less pages. But yeah, we have plenty of work here. I mean, and then we'll start the homework, the electronic homework from chapter 15 to 20, like that. All right, I think that's a better transition. All right, I'll work with you guys. So I'll send you information. All right. So what I was gonna do? Oh yeah. Okay, let me get out there and let me pull the practice package. Okay, before I go there, so my unknowns will look like this, where I give you everything in one page. You have the proton, the carbon, and the infrared all in one page. It's easier to streamline it like that. And but I was going to tell you, if you want more extra practice, you can go to this website. And here, for example, I click. Actually, let's go there so that you know what it looks like. So you can. Let's copy this. Notice that it says example 1, beginning, compound 5. So try to do beginnings and intermediate. Don't go advanced because those are really difficult ones. Those are for like advanced OCHEM students and beyond. But it looks like this. You have plenty of information where you can use for preparation for the first milestone. Plenty. Try not to knock yourself out here, okay? Because there's a lot. So if I say, for example, beginning compound 5 will be this one. So here you have the proton NMR. What I did was I copy and pasted here to make it a little more accessible, but it's still kind of fainted. But the infrared is there, is good. The infrared is there. Very nice. It tells you the major peaks, see in red. Look for those things. You'll use the chart that I provided in class. And then the carbon NMR will be there. All right, if you want to zoom out something, notice that this triplet at 77, that's your chloroform peak for carbon NMRs. Ignore that, all right? So let's say if I want to expand from, let's say, 100 to, let's see, how's that I do it? Oh, right here. So if you do like from 99 or 95 to 120, I assume that just gives me that range, which is right here, those 3 peaks. So you can play with this thing and figure it out. On my recordings, I went through this whole thing, okay? So I don't think there's a point for me to go over there. I want to teach you as much as I can here. All right, so with that said, let's do the first practice for the unknown package that I gave you. All right, so you need to use this along with, what is that? The NMR unknown chemical formulas. So I made this page separate. All right, so for my example packet, we're going to start with number 7. 7 has a molecular formula C7H8. So we're going to use that and immediately find the DU. All right, let's do that. Let's do at least one. Actually, I don't have that here, so I'm going to do it from here. From right here, right? Yes, yeah, the rubric. It's not even the key anymore. All right, so here we go. We said that was what, again? That was C7H8, thank you. So I'm going to write that down. C7H8 is my molecular formula. The first thing you're going to find is the DU. DU is 2 times 7. plus 2 because I don't have a nitrogen, minus 8, that's my number of X, divided by 2. So it's 14, 16, 16 minus 8 divided by 2 is 4. So 4 means I have most likely a benzene ring that I'm dealing with. All right? Immediately pops in my head. That's it. All right. This is my chloroform triplets here. I'm going to cancel that. I don't need that. All right? Thank you for the information. All right? So I have 1, 2, 3, 4, and 5. I have 5. Second thing I do is count my number of types of carbons. I have 5 types of carbon. And I want you to do it like this on the practice homework before you turn it in. Then the next thing we'll do is the infrared. I'll go to the infrared. Check this out. I go immediately to my 3000. Question. Oh, yeah, the magic line. Yes, exactly right. Go to the spot. The magic line is at 3000. Anything on the left side of that is sp2CHs. Anything on the right side of 3000. Just be careful here with, if you have alganaldehyde, you will have the 2 horns, but we don't have that. Anything on the right side of 3000 is sp3CHs. All right. Notice that since I have a benzene ring, most likely, which I do, because I have unsaturation of 4. I think I went too fast on that. I'll spot the 1, 2, 3, 4. Those 4 bands. This one, this one, this one, and that one are between 1630 to 1600 to 1430. Those are my C, double bond C stretch. And this one right here, those 2, I usually pick the long one. I usually say, okay, this one. But I've seen other books, people picks both of them. And that's not wrong. You just say that this is your CH band in the fingerprint region, right around 600. All right. That's pretty much it. So I go to number 4. I'm going to work on the proton NMR, and I see that I have a 5, a multiplet integrating for 5 in the aromatic region. That screams monosubstitution. I'll put an X group there because I don't know what the X is. And then I see this signal right here that integrates for 3. That must likely be a CH3. All right. So and notice that I have a total of 8 protons. Right, I have 8 protons. So and I have integration that accounts for 8 protons. So 5 plus 3 is 8. I think I can solve this puppy. I will say that this is, toluene, or methylbenzene. All right. So I would say that this is, I'm going to call this A and B, A and B, and we're good. So A will be equals to what? 7 to 8 ppms on the chart. We have a multiplet that integrates for 5 hydrogens. And B, it starts at 2.3, right, on the chart. So what I did was this one and this one. So that would be 2.3. Is a chart value. It's a singlet that integrates for 3 hydrogens. And the name for this molecule is toluene. So the next thing I'll do is to name it. Toluene or methylbenzene is also acceptable. All right. Hey, we got 2 more minutes to spare. Any questions? If not, we'll go to the lab. How many of you have lab right now? Quite a few. All right. So we got to get that going. I will see you guys next Thursday. Have a wonderful day. Question? The deadline? I haven't thought about it. Just start working on it. Good. Thanks. Yes, sir.